Good afternoon. I welcome you to this session of experimental methods in fluid mechanics, and today, in continuation of my last lecture on low pressure measurements, we will discuss today the operational principle of the Pirani gauge and the ionization gauge, and then finally we will work out one numerical problem on the McLeod gauge and how we can measure the very low pressure. That is what we have discussed. So today we will discuss about the operational principle of the Pirani gauge, and so we are writing the Pirani gauge. So this is also used to measure a very low pressure, and now we will see with a schematic depiction that how we can measure low pressure. And if you would like to measure low pressure using this instrument, what are the steps we need to follow, and of course what are the precautions we need to consider while using this device. So now I will draw a schematic diagram, then perhaps from the schematic diagram, perhaps the schematic diagram will help us to understand the operational principle of this instrument in a better way. So now I will draw the schematic depiction of the Pirani gauge. So this is a schematic depiction of a Pirani gauge, that it is having a chamber. The chamber is not closed to one, is open, and one side of the chamber is open to the vacuum, that is low pressure, that is what we would like to measure, and one filament that is there inside the chamber, and the two ends of the filament which are connected to a circuit, and the filament material is tungsten, or many a time we are using platinum as the filament material. Now so this is a typical diagram, a typical depiction of a Pirani gauge. Now this Pirani gauge is used to measure low pressure, and while we are using low pressure using this device, it exploits reduction in the effective thermal conductivity of the gas, which is at a low pressure. So I can write that this gauge exploits the reduction of the effective thermal conductivity of gas or gases with pressure, in particular in the low pressure regime. So effective conductivity of the gas will reduced, we will see how, and then if the effective conductivity of the gas is reduced, then how can we measure pressure, because the conductivity will reduce with pressure, in particular in the low pressure regime. Because I am using this sentence in the low pressure regime because at a high pressure the change in thermal conductivity with a change in pressure may not be captured correctly. So, we may not come up with a correct measurement of the pressure, that is what we are going to measure. Now, this low pressure basically in the low pressure regime, that means in order to measure the vacuum pressure, that means in order to measure the vacuum pressure. So, that is our objective is, because a very low pressure, that is what we are trying to measure using this gauge. So, the conductivity of the gas very low pressure even will be such that we can measure it. That is the objective is. Now, what we can see from the schematic, let me write again. From the schematic you can see that a chamber we have, and this chamber is containing a heated electrical filament So, a chamber which is containing a heated electrical filament, and chamber is open to a vacuum space. So, this is, and the chamber is open to vacuum space, that is clearly seen from the schematic itself. So, now the filament is connected to the circuit, and that is electrical filament. Now, I am writing next that heat dissipated, rather through the filament heat is dissipated, and this heat which is dissipated is, rather will be, that is what we need to calibrate, will be proportional to thermal conductivity or effective conductivity. So, if we now if you connect the filament, that is with the electrical circuit, whenever current is passing through the filament, then heat will be dissipated because of the electrical work. Now, that will be converted to the heat, and that heat will be heat is dissipated, and the heat, that dissipated heat which will be proportional to the effective conductivity. Now, as the pressure decreases, heat transferred away from the filament will also decrease. So, this is, now we are writing the operational principle or working principle. Okay, I can write the working principle. So, heat is dissipated, that heat dissipated, but dissipated heat will be proportional to the effective conductivity. Now, as the pressure will decrease, as the pressure decreases, then the heat transferred away from the filament, because the dissipated heat will be transferred from the filament by the to the gas, and that will decrease if the pressure is decreases. Now, if the heat transfer rate is decreased, then it is common that the filament temperature will increase. Then filament temperature increases, then the temperature of filament will increase, and this filament temperature need to measured. So, that means if I allow current to pass through the filament, there will be electrical work that will be converted to the heat will be dissipated, the dissipated heat will be proportional to the effective conductivity, and the moment when heat dissipation starts, the heat will be transferred away from the filament, and that will be taken by the gas. Now, if the gas pressure becomes low, less, then the transferred heat, the amount of heat being transferred will also be lesser, and in a way that means there is no medium to take the heat away from the filament, which will eventually results in an increment of the filament's temperature. Now, if the temperature of the filament increase, then we need to measure, and that will essentially gives us an indication of the pressure which is being reduced. I mean that is a change in pressure. So, this filament temperature is measured by measuring is obtained, I can say measured, I can say obtained by measuring its resistance in a bridge circuit. If we can measure the temperature, rise in temperature of the filament using a bridge circuit which is connected to the bridge circuit, that is what we have shown in the schematic. Then by knowing the change in temperature of the filament, we can correlate that what is the pressure, I mean change in pressure, and that too in the low pressure regime. That is what is the operational or working principle of this gauge, the Pirani gauge. So, essentially a change in temperature of the filament which is recorded by the bridge circuit will gives us an information about the change in pressure inside the chamber, and that too in the low pressure regime, and by how we can measure a very low pressure. One important thing that should be mentioned in this context, that since we are going to measure pressure or the change in pressure, gauge pressure of course, and that is very less. So, the measurement is based on this is indirect measurement of the pressure, that is a change in pressure inside the chamber is obtained indirectly because of a change in the filament temperature, and that is recorded by the bridge circuit. So, we need to mention that the environmental temperature effect may sometimes leads to error in the results which we are getting from this gauge. So, that is what now I should tell you, but I will write that environmental temperature effect on this measurement may trigger error in the results. So, that aspect should be taken into account, and I am not going to discuss in detail how we can take care of that effect, but normally what is done, similar kind of two chambers are connected in series, one is open, other is closed, and to nullify the effect that might affect the measurement of the low pressure using this device. Now from this discussion we can see that Pirani gauges are required calibration, I mean that is very important. So that means this Pirani gauge these gauges require empirical calibration. So without calibration we cannot measure, because that is what I have discussed now, that with a change in temperature of the filament we can measure a change in pressure inside the chamber. So that issue requires empirical calibration, rather the Pirani gauge requires empirical calibration, and this gauge is suitable for measuring a very low pressure, and this gauge is suitable for measuring pressure in the range from 0.1 to 100 Pascal. So this gauge is suitable for measuring pressure in the range from 0.1 to 100 Pascal, and that requires empirical calibration. While we are discussing about the working principle of this gauge, we also should discuss about the limitation and what are the possible sources of error, which if we do not take care all those, we may finally arrive at with the wrong prediction. So now a question which may arise, that is this gauge not applicable for the high pressure? Why we cannot measure high pressure using this gauge? Because this of course it is obvious that this gauge is pertinent to measure a very low pressure which is that is in the range of 0.1 to 100 Pascal, but can't we measure a relatively high pressure using this gauge? If we cannot, why we cannot? So I would like to discuss a few points for that aspect. Say what will happen for high pressure. So for high pressure we have understood that essentially a change in conductivity of the gas, thermal conductivity, that is important to measure the change in pressure inside the change in pressure, and that too in the low pressure regime, because if the conductivity of the gas is very less, then perhaps we cannot measure. I mean the rise in temperature of the heater or of the filament will increase, and if that increase, then we can measure the temperature by a bridge circuit, and from there we can correlate through the empirical relationship calibration what will be the pressure in the low pressure regime. Now for high pressure, the change in conductivity, the change in conductivity is very small. So for high pressure, change in conductivity is very small, and if the change in conductivity is very small, because essentially a change in conductivity, rather reduction in thermal conductivity with gas, that is the key theme of measuring low pressure using this gauge. Now if that is the case, then heat loss from the filament, heat loss from the filament is not so significant such that rise in temperature of the filament, so such that a rise in temperature of filament is not appreciable. So, this is very important, that because of the conductivity change of the gas, if it is very less, then perhaps the heat loss from the filament is not significant. So, because there should not be any heat transferred by the gas, so conductivity is very less. So, the rise in temperature of the filament is not appreciable, that will be measured by captured by the bridge circuit, so that we can measure the pressure. So, the high pressure issue, high pressure. So, heat loss from the filament is function of the conduction loss. Heat loss from the filament is function of the conduction loss to the filament and radiation loss to the surroundings. So, this is the issue, that heat loss from the filament is function of the conduction loss to the filament and radiation loss to the surroundings. That means, for the high pressure the change in conductivity is very less, right, change in conduction is very less, very small, and since the heat loss from the filament in that case becomes function of the conduction loss and also up to the filament and also the radiation loss to the surroundings. So, that means for the high pressure we cannot measure, because for the high pressure that means this is very important to know, that there will be a significant change in the conductivity, thermal conductivity of the gases, otherwise we cannot measure a low pressure using this device. And for the high pressure, this conductivity of the gas is not so significant that we can measure the change in pressure using indirectly by measuring the temperature of the filament. In that case, temperature of the filament will not, there will not be an appreciable change in the temperature of the filaments, so that we can record using bridge circuit. Effectively we won't be able to capture the change in pressure correctly. So, this is what is the restriction of this device. And another important is that the transient response of this device is very poor, because this we should know, that transient response of this gauge is very poor, and attaining equilibrium needs several minutes. At low pressure. So, this is another important point that I would like to discuss, that the transient response of this gauge is very poor, because if you need to attain equilibrium, which require several minutes at the low pressure. So, it cannot give us a transient response. That means, if you would like to measure a change in pressure, so measurement of a change in pressure, transient measurement of a change in pressure is not, this gauge is not appropriate for the transient measurement of a change in pressure, because the working principle by which the gauge works, which requires several minutes time to reach at the equilibrium at low pressure. Otherwise, we won't get the correct result, it will continuously fluctuate. So, these are the restrictions, limitations of this gauge. and typically this gauge is used to measure a pressure which is that is what I said, that from 0.1 to 100 Pascal. And again I am telling, whoever will be using this gauge to measure low pressure, of course in the regime of low pressure he or she needs to use this very cautiously, and not only that, because we need to measure everything correctly, otherwise we won't get the result correct, we won't get the result rather perfect results. So with this we have discussed about two gauges which are used to measure low pressure. First one I have discussed in my last lecture, that is the McLeod gauge, and today I have discussed about the Pirani gauge, and both these gauges are used to measure low pressure, and we have discussed about their working principle. Also we have discussed about their about the limitation, about the restrictions of using this device in measuring pressure. Now today we will work out one numerical problem on the McLeod gauge, that is what we have discussed in the last lecture. Now McLeod gauge, if you can recall, that we have seen that this gauge is also used to measure a very low pressure, I mean in the regime of low pressure, that is what we have discussed. And this McLeod gauge again, if you can recall that the reading in the capillary tube, if you can recall, that is what we have discussed clearly, that we can have the movement of the reservoir, and by having movement of the reservoir we can alter the level of the mercury in the capillary and reference capillary, and by allowing the vacuum pressure, very low pressure into the system, then again if we try to we try to bring the reservoir in its original position, then we can measure the low pressure. Now today we will work out on numerical problem, and for that, and let me write the problem statement, then we will see how we can work. So the problem on the McLeod gauge. So I am writing one numerical problem. A McLeod gauge has a capillary diameter of 0.2 millimeter and a volume, that is bulb volume, volume VB is equal to 125 centimeter cube. Now question is, what gauge reading will result for an absolute pressure of 20 micron. So a McLeod gauge has a capillary diameter of 0.2 millimeter and a volume VB, that is the bulb volume. If we try to recall the schematic of the McLeod gauge, then this VB is the bulb volume 125 meter cube. Then we need to calculate what gauge reading will result for an absolute pressure of 20 micron, results for an absolute pressure of 20 micron. So this is the question. Now we have to solve this problem. So now we will try to solve, but for that at least it would be nice if we try to just recall the schematic of the gauge, and it will help us to understand the problem in a better way. So now we have seen that we have this small capillary, then we have kind of thing, and then just I am trying to draw the schematic. This is not again at per scale. And this is from vacuum, this is P, and this is the closed end capillary, that is now, and say this is the mercury, and this is connected to one movable reservoir. So, this is movable reservoir, and this is valve, this is capillary, and this is reference capillary. And this is opening O, if I can recall. Now, this is what we have discussed in the last class, that there are operational, the working principle of this McLeod gauge. Now, the problem is very easy. Now, if you would like to solve this problem, for this problem the volume VB, the VB is essentially, if you can recall, the VB essentially the volume of the branch containing the valve, that is what we have discussed in my last lecture. This is the volume of the branch containing the valve above O. So, volume of the branch containing the valve above O. So, this is the VB. So, that means there are two different branches, one is with the capillary, other is connected to the reference capillary. Now, VB is the volume of the branch which contains, rather containing the valve above O. Now, VB is given, that is 125 centimeter cube, that is 125 centimeter cube, and that is 125 into 10 power cube millimeter cube. Now, we know from our previous lectures, from my previous lecture, we know that the pressure P is AY square by VB, and to arrive at that expression we have assumed that the VB, and that is, if you can recall, we have discussed that the VB is much smaller than the AY, that is the length of the mercury containing in the capillary, that is AY, that is A is a cross section area, that means VB is, VB is much larger than AY. A is the cross section area of the capillary, and Y is the capillary distance, that is what we would like to measure, right. Y is the capillary distance, length of the region containing the gas, length of the region containing gas is Y. So, now that is what we have to measure, Y we need to measure. So, Y is the length, is very important. Y is the length of the gas, length of the region containing, gas above the that is what in the capillary. Now, if and that relationship we have derived, now we need to know, if we look at the question, that what gauge reading will results for an absolute pressure of 20 micron. That means P is given, that pressure of 20 micron, that 20 into 10 power minus 6 meter, and 20 into 10 power minus 3 millimeter. So, now Y we can directly get from this expression, 1. So, from equation 1 we get Y square is equal to VB into P divided by A. So, we can calculate 125 into 10 cube, that is the VB, and P, that is the absolute pressure of 20 micron. Now, long back I told that these gauges are also many a times we can use, if you can recall that when I have discussed about the pressure measurement, that how we can measure absolute pressure, gauge pressure we have defined, and then we have discussed that we are many a times we are using this kind of this aneroid barometer, right. This aneroid barometer is advantage is that we have discussed that the measurement of the gauge pressure, which is sometimes the absolute pressure measurement is directly related to the measurement of gauge pressure, that is what we have discussed. Now, this is 125 into 10 cube into, that is P is equal to 20, 20 into 10 power cube, that is what we have written, to 20 into 10 power minus 3 divided by A, that is pi by 4 into 0.2 square, because it is given that 0.2 millimeter is the diameter of the capillary. So, if I calculate it, we will get Y is equal to twice 82.16 millimeter. So, this is the gauge reading for an absolute pressure of 20 micron. That is the beauty of this kind of gauges, that if you would like to measure absolute pressure, we can. So, for the measurement of 20 absolute pressure, the gauge reading will be 286.16 millimeter. So, now if we know the gauge reading, from there again we can calculate what will be the absolute pressure, that is what we can measure using this kind of Macleod gauge. So, today to summarize, today we have discussed about another one type of low pressure measuring gauge, that is the Pirani gauge. We have discussed about the working principle of the Pirani gauge. Also, we have discussed about the limitation of this gauge, and also finally we have discussed about that if someone would like to use this gauge to measure pressure which is in the regime of low pressure, then he or she should take special care while measuring the reading to measure the temperature change, since the change in temperature will directly give us the change in pressure within the chamber. And finally, we have solved one numerical problem on Macleod gauge. From there, we have seen how we can measure the absolute pressure in terms of measuring the length of the region containing the gas. So, with this I stop my discussion today, and we will continue our discussion in next class. Thank you.